Hello, AP Chemistry students. We're now on Unit 7, Part 1 on reversible reactions. And this is going to cover sections 7.1 through 7.8. So Unit 7 is all about chemical equilibrium, which is a concept you probably haven't learned about in prior chemistry classes. So we're going to go over all of the basics. So the learning objectives here are to explain the relationship between the occurrence of a reversible chemical or physical process and the establishment of equilibrium to experimental observations, to explain the relationship between the direction in which a reversible reaction proceeds and the relative rates of the forward and reverse reactions, to represent the reaction quotient QC or QP for a reversible reaction, and the corresponding equilibrium expressions Kc equals QC or Kp equals QP, to calculate Kc or Kp based on experimental observations of concentrations or pressures at equilibrium, to explain the relationship between very large or very small values of K and the relative concentrations of chemical species at equilibrium, to represent a multi-step process with an overall equilibrium expression using the constituent K expressions for each individual reaction, to identify the concentrations or partial pressures of a chemical species at equilibrium based on the initial concentrations and equilibrium constant, and then lastly, to represent a system undergoing a reversible reaction with a particle model. Sorry, that was a lot, but there's a lot of small bits to cover here. So some chemical and physical processes are reversible, meaning they can go either way. They can move forwards to the products or they can go backwards back to the reactants. And they're usually indicated by the double arrow symbol in a chemical equation. Two big examples of this would be phase changes, where we're going from solid water to liquid water. And this can also go backwards depending on the temperature or the external forces. And then things like acid and base reactions, where you have trades of protons that can go back and forth. For example, ammonia reacting with water to make ammonium and hydroxide. This hydrogen from the water goes on to the ammonia to make ammonium by pulling it off of the water and making hydroxide, but this can also go in the reverse direction. And the rate at which the forwards reaction towards the products and the reverse reaction towards the reactants can be controlled by the system's equilibrium. Now, what does equilibrium mean in terms of chemistry? Well, the general definition of equilibrium is defined as a state of rest or balance due to the equal action of opposing forces, or the equal balance between any powers, influences, etc., equality of effect. This picture gives me anxiety just thinking about it, but this is I think he was a French guy who did a tightrope walk across the World Trade Centers when that was still a thing. Um, and he's using a physical equilibrium to balance by making sure that the forces acting on this pole balance out the forces acting on his body. However, in chemistry, the forces being balanced are not the amounts of reactants and products on both sides, but rather the forces pushing a reaction to create the reactants or the forces pushing a reactant to create products, which are controlled by kinetic collisions. So let's look at a little demonstration here. I want you to watch this video and think about, when does this system reach equilibrium? So there's two beakers. He has two smaller beakers, one big, one small. He's going to start pouring the liquid from one into the other, and then using the smaller beaker to pour it back to indicate that this is reversible. But this already does tell us that the way in which reactants are becoming products is not the same in which the products are going back to make reactants. So we can start to see that the second beaker is starting to fill more and more until we've kind of reached an equality point, but now it keeps going. Now you'll notice that he keeps pouring them back and forth, but the overall volumes of the solutions aren't really changing anymore. There's a steady smaller amount over here and a steady bigger amount over here, no matter how many times he pours from one into the other. And that's the main point I wanted to show here. So you might have instinctually answered that we reached equilibrium when the liquid levels were equal, which happened around 39 seconds. However, as he kept pouring from one into the other, the levels kept changing until around about 50 seconds in, when we got that small amount in the first beaker and that larger amount in the second beaker, in which things stopped happening. This is actually the point in which the balance occurred. And it had a lot to do with the sizes of the beakers he was using to pour them back and forth. The one he was going from the left beaker to the right beaker was much bigger than the one going for the reverse. And this is sort of an analogy to chemical equations. Sometimes the kinetics that push a reaction forward are not the same as the kinetics that push a reaction backwards, which doesn't mean that balance cannot be achieved between those two forces. So in chemistry, unequal amounts don't necessarily mean unbalanced between the forces of creating reactants and creating products. So chemical equilibrium is defined as when the forward and reverse rates of a reversible chemical reaction are equal and the concentration of reactants and products stop changing. So a good way to think about this is in terms of these graphs down here. We indicate that a system of, say, A becoming B and B going backwards to A are at equilibrium when the rate of formation of A is equal to the rate of formation of B. And we can see that in this graph here, where we are graphing rate as a function of time. So we start with a high forward rate as our reactants start to become products, and that decreases over time, like we saw in most first or second order reactions. And then in this reverse rate, it starts to increase over time until it reaches this purple point where the rates have become equal. And this is considered to be at equilibrium. And in terms of the actual reactants and products, equilibrium will appear as if nothing is happening. And that's kind of what we saw in the video. We reached equilibrium when the water levels were no longer changing. And what that looks like on a graph, here we have the amount of reactants and products graphed as a function of time. And our reactants slowly start to decrease as our products start to increase. And then once we've reached the equilibrium state, the amount of reactants and the amount of products, even though they're not the same, we have more products than we have reactants here, they have stopped changing. They have started to balance out. And in general, if the rate of the forward reaction is greater than the rate of the reverse reaction, it will continue to favor making products. That's kind of like this part of the graph. And if the rate of the reverse reaction is greater than the rate of the forward reaction, it'll continue to make reactants, which would be sort of like a backwards version of this. And at equilibrium, the rates become equal, even if the amounts of reactants and products are not, which we've shown a couple times now. So let's try to interpret this following model of N2O4 dinitrogen tetroxide in a reversible reaction with nitrogen dioxide. So we have some similar graphs here that we saw before. And if we track this dotted line on the x-axis, we could see that it is showing 3 different points in time. One at the beginning of the reaction, one in sort of the middle of the reaction, and then once we've reached equilibrium. So in our first state, we have all N2O4. So we haven't formed any NO2 yet. And then in the middle state of the reaction, we could see that some of our particles have now collided and split up into make NO2 molecules. And then when we reach the equilibrium point, we have a lot more NO2 particles. And it looks like the amount of NO2 particles are now exceeding the amount of N2O4 particles. And then here we could see the concentration as a factor of time, sort of zoomed in at the equilibrium state. Our reactants have decreased over time, our products have increased over time, and once we reach equilibrium is when those two states have leveled off. And then for the rate as a function of time, the forward rate starts higher than the reverse rate, and then eventually they even out when we reach equilibrium. So if we're going to figure out how this works mathematically and how we can predict what equilibrium is going to look like for a system, we need to refer to something called the reaction quotient, which is defined as Q, and the equilibrium constant, which is represented as K. And if we were to consider a generic chemical equation where we have A plus B in a reversible reaction with C plus D, all with coefficients in front of them. These lowercase letters represent the molar coefficients. The way we would determine the reaction quotient or the equilibrium constant is with the following expressions, where the Q or K is equal to a ratio of the product of the amount of products, so product meaning multiplication, over the product of the amount of reactants, each raised to the power of their stoichiometric coefficients. So, for example, the products here are C plus D, so it's C plus D raised to the power of little c and little d, which are their molar coefficients. If we're at equilibrium, and if all of these amounts are the equilibrium amounts, the thing is equal to K or KEQ. And if it's not at equilibrium conditions, if we still haven't reached equilibrium yet, it's represented as Q. And these things are gonna make sense a little bit later. So if Q is less than K, if the reaction quotient for the non-equilibrium conditions is less than K, that means that the ratio is more reactant favored, is more denominator favored than the products, which represent the numerator. Then the reaction is still going to shift right to the products because the Q is going to want to eventually equal K for it to be at equilibrium. And if Q is greater than K, that means it's more numerator favored than the equilibrium wants to be. So it's going to shift to make more reactants in order to make the denominator bigger and then decrease the Q value until it equals K. Because when Q equals K, that's when we know the system is at equilibrium. K and Q themselves are unitless values, so you're never going to have to tell me what the units of these are. And they represent the relative likelihoods of the forward and reverse reaction. Basically, the magnitude of it, how big they are, tells us something about the likelihood of the reaction proceeding. And one important note is that these are usually in concentrations. So the pure solids and pure liquids that might appear in a chemical equation are usually omitted from these expressions when calculating Q and K, because a pure solid or a pure liquid is not something dissolved within something else. It doesn't have a concentration that we can even plug in. So the concentrations of pure liquids and pure solids are independent of the equilibrium. And lastly, as I was kind of hinting at before, the larger the K value, the more product favored it is because it's more there's more numerical magnitude in the numerator than the denominator. And these are reactions that proceed mostly to completion. So if a reaction has a high K value, you can expect that most of the reactants are going to turn into products. If you have a really small KEQ, it's going to be reactant favored, meaning some of the reactants will be converted to products, but mostly it'll stay on the reactant side of the reaction. And if some products are made, they might reverse back into reactants. And if we were to think about the liquid demonstration I showed you earlier with the green liquid, that would be a highly product favored reaction with a large K, because you saw that at the end, there was a lot more product than there was reactant. And the rate the rate that was pushing forward to the products, which was represented by a bigger beaker. So KEQ, the equilibrium constant, represents a general equilibrium constant. But you'll see different subscripts on the K if we're talking about different types of equilibrium. For example, Kc, which is probably one of the most common ones, represents solution equilibrium or concentration equilibrium, which I think the C stands for. And values in these expressions are in molar concentration. So if you're calculating the value here, all of the values for C, D, A, and B that you're going to plug in are going to be in molar concentration values. There's also Kp, which represents a gaseous equilibrium. And gases are usually measured as pressure to know how much gas there is in a system. So these values are usually expressed in pressure units, either atmosphere, kilopascals, or millimeters of mercury. You'll also see Ksp, which represents a solubility equilibrium, which relates to how soluble or insoluble something is. And we're going to cover this a lot more in part 2 of Unit 7. And then there's also KB, Ka, and Kw, which are equilibria relevant to acids and bases. And this is going to be covered a lot more in Unit 8. So let's look at an example of making an equilibrium expression and calculating K. And let's do so for the following reaction of 2xy aqueous plus zw aqueous in equilibrium with zy2 aqueous and x2w solid. So what is the value of Kc if the equilibrium concentrations of xy, zw, and zy2 are all 0.1 molar? Also, we're going to answer, is the reaction reactant or product favored? So first off, we're going to make an equilibrium expression of our Kc value being equal to the ratio of the concentrations of the products over the concentrations of the reactants raised to the power of their coefficients. And that's going to look like this, where Kc is going to be equal to Zy2 as concentration, and then we omit the X2W concentration because it's a pure solid, so it doesn't have a concentration to plug in. So that's going to be removed from the expression. And that's going to be over both reactants, which are XY and ZW. And since XY had a molar coefficient of 2, it's going to be raised to the second power. Now, we know that the equilibrium concentrations of all three of these substances in the expression are all 0.1 molar. So we plug in 0.1 molar for all of them. And then we calculate, and we get a Kc value of 100. So this is a fairly big equilibrium constant. So we can assume that this is going to be product favored. A good way to check this is if it's greater than 1 or less than 1, because that'll tell you which part of the ratio is being favored, either the products or the reactants. All right, let's look at another one. Let's calculate Kp for the following reaction of hydrogen gas plus iodine gas in equilibrium with 2 hydrogen iodide gas. And we know that the equilibrium concentrations are 0.1 atmospheres for both hydrogen and iodine, and then 2.83 atmospheres for the hydrogen iodide. So much like the expression before, the Kp, our pressure equilibrium constant, is going to be equal to the amounts of products over reactants, everything raised to its molar coefficient. But in this time, we're going to be plugging in pressure units instead of concentrations. And a common way that's expressed is with a capital P with a subscript of the chemical itself. So Kp is going to be equal to the pressure of hydrogen iodide to the second power over the product of the pressures of hydrogen and iodine gas. And then I can plug in my pressure values for each substance. And then I get 801, which is a pretty big equilibrium constant. So that means that this process is highly product favored. All right, and let's consider this reaction. If we have 2A plus B in equilibrium with 3C, we know that our equilibrium expression is going to be products over reactants, each raised to their molar coefficients. And say we know that equilibrium, A's concentration is 0.2 molar, B's concentration is 0.4 molar, and C's concentration is 0.8 molar. We can calculate KEQ by plugging in the concentrations into the equilibrium expression, and we get 32. But say I'm also given initial conditions. Say that the reaction is starting with a 0.8 molar solution of A, a 0.1 molar solution of B, and a 0.C molar solution of C. Then since this is not equilibrium concentration, this is going to be calculating the reaction quotient Q instead of K. And the value of Q here is going to be 1. So now we can think about the relationship between KEQ and Q. Since Q is smaller than KEQ, that means that this part is more product favored. It wants to be more product favored because to get to equilibrium, Q is going to want to be equal to K. So in order for 1 to become 32, it's going to have to become a lot more numerator favored. So it's going to want to become more product favored. And therefore, if given a mixture of solutions under these initial conditions, this is going to shift to make more products until the value of Q becomes equal to the value of KEQ. Let's look at another similar example. So here we have carbon monoxide reacting with water vapor in equilibrium with carbon dioxide gas and hydrogen gas, and say that the pressure equilibrium here is 1. Let's figure out what's going to happen under the following conditions of 1 atmosphere of carbon monoxide, 1 atmosphere of water vapor, 2 atmospheres of CO2, and 2 atmospheres of hydrogen gas. Well, I'm going to set up my reaction quotient expression, so products over reactants, and then I can plug in all of my amounts under these conditions. So the two products were 2 atmospheres and the two reactants were 1 atmosphere. So we have 2 times 2 divided by 1. We end up with a quotient of 4. And in this case, our quotient is bigger than our K value, which means it's more numerator favored than it wants to be, which means that since Q is bigger than K, the reaction is going to shift back towards the reactants in order to even it out. And this is going to happen until Q becomes 1, and then it becomes equal to the K value. So what about the equilibrium of multistep reactions? Well, similar to Hess's law, you can manipulate and sum up equations to calculate KEQ for a multi-step process. However, the rules that we used for Hess's law are not going to apply here. We're going to have to apply different rules for how to sum up our KEQ values to get a equilibrium constant that represents the sum of multiple steps. So if we're going to reverse a reaction in order to get a different KEQ, instead of flipping the sign, we're going to take the reciprocal of it. We're going to do 1 divided by KEQ. If we're going to multiply a reaction by a coefficient or a value, we're going to have to raise the KEQ to that power. And then when we're adding the reactions together, we're going to need to multiply their KEQ values together. We're going to have to take the product of the KEQs rather than adding them. So let's review the algebra for why this makes sense. So say we have an equilibrium between A and B. Our equilibrium constant is going to be equal to the concentration of B over the concentration of A. But say we wanted to reverse this reaction, then we're going to have B becoming A in equilibrium. And our K value is going to be now A over B. And if you compare K1 to K2, well, K1 to the minus 1 power, the reciprocal of K1 is going to be equal to K2. So to reverse the reaction, we had to take our equilibrium constant and raise it to the negative 1 power, or take the reciprocal of it. Now, say we had 2A in equilibrium with 2B. Well, this is just the first reaction here of K1 multiplied by 2. So if we were to write a new equilibrium expression to make K3 here, now we're going to have B to the second power over A to the second power. And this is going to look a lot like A, or a lot like K1 if we squared the whole thing. So that means that if I multiply the equation by 2, I'm going to then take the equilibrium constant and raise it to the power of 2. And then say we had C in equilibrium with D. Well, this is obviously going to be products over reactants, so D over C. But say we wanted to combine A becoming B and C becoming D into one bigger equation of A plus C becoming B plus D, and we were to write a equilibrium expression for that, our equilibrium constant would be B times D over A times C. And that just looks like we took K4 and K1 and multiplied them together and smashed them together. So the equilibrium constant for the sum of these two processes would be the product of their two equilibrium constants. So let's look at an example of this. So say we wanted to calculate KEQ for the following reaction. We have sodium chloride plus silver ions making sodium ions and silver chloride. So we have a single replacement redox type reaction. Well, if I look at the relationships between sodium chloride and sodium ions, and then silver chloride and silver ions, I can find some K values. So sodium chloride dissolving to make Na plus and Cl minus has a K of 36, and then silver chloride splitting up to make silver ions and chloride ions has a K value of 1.8 times 10 to the negative 10. So this one's pretty product favored, but this one is pretty reactant favored. And I can use these two and manipulate them and sum them up to get the target equation, much like we did with Hess's law before. So in order to get a sum up, I'm going to need to cancel out the chloride ions, and I'm going to need to get the silver chloride on the product side. So I can do all of that by reversing this second equation here. And if I flip the second equation, I'm going to need to take the reciprocal of the K value. So 1.8 times 10 to the negative 10 raised to the negative 1 power gives us 5.5 times 10 to the 9. And this makes a lot of sense that our small value became a huge value because something that is not very product favored is going to be a lot more product favored if we flip it around. So then we're going to sum them up. So we're going to sum up our reciprocal K2 value for the flipped second reaction, and we're going to multiply that with K1, which was our NaCl equation. So then K1 times K2 to the first negative 1 power will be 36 times 5.5 times 10 to the 9, and overall we get 2.0 times 10 to the 11, which tells us that overall this is a very, very favorable reaction. At least in terms of pushing it towards the product side. All right, let's try another one. Let's calculate KEQ for the following reaction of 2 NaCl plus lead ions, making 2 sodium ions, and lead 2 chloride. And we are going to use similar starting information. We have the same equation from the last time. We have sodium chloride dissociating with a K of 36, and then lead's dissociation constant, or lead 2 chloride's dissociation constant is going to be 1.6 times 10 to the negative 5. So this time I'm going to have to multiply the first one by 2 so that we can cancel out 2 chlorides in both of them. And then much like in the last case, I'm going to have to inverse this second reaction or reverse this second reaction and get the reciprocal of the K value. So by multiplying the first expression, oops, I should have 2 there. I'm going to get a K value of K1 to the second power, which is going to be 36 squared, which is 1296. And then for the second one, since all I need to do is flip it, I'm going to take the reciprocal of the K value, which is going to be 1.6 times 10 to the negative 5 to the negative first power, which is going to give us 62,500. And then finally, to get KEQ for the whole summed up process, I'm going to need to take the product of K1 squared and K2 reciprocal, which is going to give us 8.1 times 10 to the 7th power. If we consider this equilibrium, this makes a lot of sense if we compare it to solubility rules. You might remember that lead halides and also silver halides, like in the example before, are highly insoluble. They generally form precipitates when lead or silver ions come in contact with halide ions. And that makes a lot of sense that our KEQs are very large numbers because it means that the formation of those precipitates, which are the products in both of these reactions, are highly favored. So earlier we related the equilibrium constant and the reaction quotient to the equilibrium concentrations, but we're not always going to know what the equilibrium concentrations are. So how can one quantitatively relate initial concentrations, equilibrium concentrations, and K? Well, we can do so using stoichiometry and something called an ICE table or an ICE table. And this stands for initial, change, and equilibrium. And these are really similar to BCA tables if you've ever done that as a way to help learn stoichiometry. So consider the following reaction of 2A plus B in equilibrium with 3C. The table for this reaction will be set up like this, where we have 2A plus B in equilibrium with 3C, so a column for each substance, and then we'll have a row for the initial concentrations, a row for the relative change, and then a row for the equilibrium concentrations. So let's look at a specific problem involving this reaction. So say the starting concentrations of A and B are 0.5 molar, and the equilibrium concentration of A is 0.1 molar. What are the other equilibrium concentrations, and what is the equilibrium constant? Well, we know that the initial concentrations of both A and B are 0.5 molar, and the starting concentration of C is going to be 0 because it hasn't been formed yet. And we know that the equilibrium concentration of A is 0.1 molar. We can actually figure out everything else on this table and then also figure out Kc just based off of the stoichiometry. If we look at the mole ratio, we can infer that for every mole of B that gets used up, 2 moles of A will be used up, and 3 moles of C will be formed. And we can reflect that in the change row. Because if we lose 1x of B, we're going to lose 2x of A and gain 3x of C. And the whole key to this is going to be the 0.1 molar here. It's almost like a Sudoku. Um, we know that the change for A was minus 2x, and the difference between 0.5 and 0.1 was 0.4. So therefore, if 2x is equal to 0.4, then x is going to be equal to 0.2, which means that the change in concentration of B is going to be minus 0.2, and the change in concentration of C is going to be 0.2 times 3, or 0.6. So then we end up with an equilibrium concentration of A of 0.1, equilibrium concentration of B of 0.3 molar, and then an equilibrium concentration of C of 0.6 molar. And then finally, we can use those equilibrium concentrations to solve for Kc by making an equilibrium expression. So Kc is being equal to the products over the reactants, all raised to the power of their coefficients. And then we can plug in all of the equilibrium concentrations we found, and we end up with an equilibrium constant of 72. Now, say we want to calculate the equilibrium concentrations of all of the substances using just the starting concentrations and the equilibrium constant. And this time, let's consider the reaction of AB in equilibrium with A plus B. And we're going to calculate the equilibrium concentrations when the starting concentration of AB is 0.8 molar and the equilibrium constant is 3.0 times 10 to the negative 14. So all we know this time is the starting concentration of the reactant and the constant. But we can use the same logic as before to infer the rest. So we have our initial concentration of 0.8 molar for the reactant. I start with nothing for both of the products. And if I look at the stoichiometry, everything is in a 1-to-1 ratio. So if I lose 1x of AB, I'm going to gain 1x of A and gain 1x of B. And then 0.8 minus x is going to give me an equilibrium concentration of 0.8 minus x. We're going to solve for x later. And then both A and B start with nothing, and they both gain x, so they're both going to have equilibrium concentrations of x. So then I can make an equilibrium expression using these equilibrium concentrations with the x in them and solve for x as a variable using the equilibrium constant. So that's going to look like this, where I have 3.0 times 10 to the negative 4. It's going to be equal to A times B, which are both x, divided by 0.8 minus x. And if I do the math here, I'm going to end up with a quadratic equation that looks like this, where I have 0 is equal to x squared plus 3.0 times 10 to the negative 4x minus 2.4 times 10 to the negative 4, which is the product of 0.8 and 3.0 times 10 to the negative 4. And this is a pain. I don't want to have to solve a quadratic equation here. Well, luckily the AP exam doesn't require you to solve quadratics for these types of problems. I've heard that sometimes they'll make you do it if it's a perfect square, but I haven't actually seen any problems like that before, but just keep that in mind. But we can make some assumptions here that'll make this easier and make us not have to use a quadratic. And the assumption we're going to make is that the value of x is going to be super small relative to the other values. The amount that we're going to lose of our reactant, especially since the reaction constant is 3.0 times 10 to the negative 4, which means it's pretty reactant favored. We can assume that we're not going to lose very much of it, and the value is going to be negligible. So what we're going to do is in the denominator, the amount that the reactant is losing is going to be negligible relative to the amount that we start with. So this minus x in the denominator, we're going to ignore and omit. And we'll end up with just x squared over 0.8 is equal to 3.0 times 10 to the negative 4, which is much, much easier to solve. And we can end up solving x as 1.5 times 10 to the negative 2. And we can see that this value is a lot smaller than this value, and our assumption is valid. So therefore, our equilibrium concentrations of A and B are both going to be 1.5 times 10 to the negative 2 molar, since we were solving for x, and x is what we predicted their concentrations would be based off of our ICE table. And then to find the concentration of AB, it's going to be 0.8 minus x, so it's going to be 0.8 minus 1.5 times 10 to the negative 2, and that ends up with 0.79 molar. All right, let's do one more example. Let's consider the following equilibrium of hydrogen fluoride or hydrofluoric acid in equilibrium with hydrogen ions and fluoride ions. And let's consider that our equilibrium constant is 6.6 times 10 to the negative 4. If enough hydrogen fluoride or hydrofluoric acid is added to a solution to have a starting concentration of 1.05 molar, what will the concentration of each of the dissociated products be when equilibrium is reached? So pretty similar to the last problem. Let's set up an ice table. So we have hydrogen fluoride in equilibrium with hydrogen ions and fluoride ions. We start with our concentration of 1.05 molar for the HF. We're going to start with nothing on the product side. And since this one is also all 1-to-1 ratio, we're going to lose 1x here, we're going to gain x here, and we're going to gain x here. And our equilibrium concentrations are going to be 1.05 minus x molar, and then x molar for both hydrogen ions and fluoride ions. And much like before, I'm going to set up an equilibrium expression using my equilibrium constant. So I'm going to have x squared on top because I'm going to have x times x for the products over 1.05 minus x. And then using that assumption from before, I'm going to omit x in the denominator. So then I'm just going to end up with x squared over 1.05. And then I can solve. I can multiply 1.05 by 6.6 times 10 to the negative 4, and then square root the whole thing. Um, Putting something to the half power is the same as square rooting it, if you weren't familiar with that. And then I end up with 0.0263 molar as my value for x, which means that the concentrations of hydrogen ions and fluoride ions are both 0.0263 molar. And then my concentration of the hydrofluoric acid is going to be 1.05 minus 0.0263 molar. And that's going to end up with 1.02 molar overall. All right, and that's going to do it for part 1 of Unit 7. So I'll see you in the next one.